Hello, welcome to the STA 371G Homework 9 R-Help video. Today we'll be going over the car package and the Durbin-Watson test function, time series scatter plots, the forecast package, absolute percentage error, simple exponential smoothing, time series models, various model types, and mean absolute percentage error and the metrics package. So to install the car package, type install.packages and car in quotations. This is the general format you'll use for any package, but instead of car, you'll type what the package is. You only have to install it once, but to use it, type library car. That goes for any package as well. Just type library and the name of the package. You'll do that every time you use it. A function in the car package is the Durbin-Watson test. The format for this is Durbin-Watson test, capital W and capital T, and then the name of the model. Once you run that function, you'll be able to see the p-value in the Durbin-Watson statistic, which is helpful. Next, to make a time series scatter plot, you use the same format as you would if it weren't time series data. So you type plot x comma y or y tilde x. Remember that the x should always be the year or the time, whatever measurement it's in. So if we run that, we can get the scatter plot, year, and whatever the output is. To install the forecast package, do the same thing I mentioned earlier and run library forecast. The forecast package contains the MA, the moving average function. The format for the moving average function is whatever your data is, $, whatever variable you're looking at, comma, order equals, and this number is going to be the units. So for example, if it's a 2-point moving average, you would write 2 here, a 3-point, you'd write a 3. It could also be called a 2-year or a 3-year, etc. Comma, center equals false. If we run that, we get our moving averages down here. To find the absolute percentage error, use the following formula. Actual minus predicted divided by actual multiplied by 100 to get it as a percentage. You could just type the numbers, so 1.071 minus 1.061, the quantity of which is divided by 1.071, and multiply that by 100. I find it's easier though to use vectors and then run this command to do it more efficiently. So we can see it's 0.934 is our absolute percentage error. To make the SES or simple exponential smoothing model, you'll use the following format. Whatever you want the model to be called equals SES, whatever data you're using, $, whatever variable you're using, comma, alpha equals, and then the level. It will be given in the question, so you don't need to worry about coming up with that yourself. Once you run that command, simply type ses.model or whatever your model's called, and you'll get your forecast, which is this first column. To make a time series model, if you want to create a plot, you can write whatever you want it to be called equals TS, data, $, the variable you're using, the start year, and the frequency. So for example, this one, I said the start is 1999 and the frequency is 4. If you look at the data, the year is 1999 and it's quarterly. So for example, if it were semi-annual, you would use frequency equals 2 and modify the start year, and then plot, whatever you call it. So you don't necessarily need to plot everything, but it's useful to know how if you'd like to visualize what it looks like. To create the lags, the best way to do so is whatever your data is called, $, the lag you're creating equals C, and then the NA will correspond to what lag it is. So if it's lag 1, you'll write 1 NA. For lag 2, you'll write 2 NAs, comma, the variable, and then in brackets 1 through n minus the lag. So if we look at the data, we can see there are 25 entries. I'll highlight it here. It will be different for whatever data you're using, so this is dependent on that, but let's just say it's 25. So to create lag 1, 25 minus 1, since it's lag 1 is 24, so we'll put 1 to 24. For lag 2, you would do 25, because 25 observations minus 2 is 23, so 1 to 23. So that's how you create lag 1 and lag 2, and create the model. Model equals LM, y tilde your x's, which are going to be your lags, comma, data equals data. And then you can use the sum functions like summary model or just type model to get coefficients or that kind of thing. You get your estimates, p-values, standard errors, etc. To create the exponential or multiplicative model in the homework that has the formula log price equals intercept plus slope times time, you'll do the following. First, I'd like to point out that this model wants you to use log base 10. Typically, when log is said in statistics, it's referring to natural log base e. But in this, it's log base 10. So you'll use the log base 10 command instead of just the log command. This command right here is creating a variable for the log price, which is going to be our response variable, by taking log 10 of whatever variable. So this line is just to create the response variable. Once we've created the response variable, we can have our exponential model, whatever name you prefer, equals lm log price, because it's the response I created, tilde time, because time is what the time component is called in this, which is the x, data equals data, and then run our model and we can get our coefficients. I'd like to point out to remember to use this format instead of data $ log price or data $ time, because you can use the predict.lm function if you do it this way, which will be helpful later. You could also do it in one step if you wanted to do log base 10 the price. What this does is it cuts out the necessity of doing this and creating the variable. So you can either do it in one line like this or in two lines like this. But it works the same and you get the same results. To make the autoregressive model, whatever you want to call the model equals lm data $, whatever it is, or you don't need the data $, which we have data equals data right here, but we can run our model and do summary model and we get our coefficients. Again, notice how there was no data $, it's just data equals data. And this doesn't just have to be lag 1, you could always add plus lag 2, plus lag 3, etc. for however many you wanted. The metrics package is a useful tool to calculate MAPE, or mean absolute error percentage. Once you install the package, you'll need to use library metrics, and then we will go over how to use the command. So the format for MAPE is actual, predicted. The actual values come from the data. The predicted values come from the predict.lm function, which is why it's a necessity to type data equals data instead of data $ to specify the column. Once we run predict.lm, for example, the model I created above, model C, we can see that it predicts the values from 2 to 25 because it was a lag 1 model. So for example, let's say for our exponential model, we want to find the mean absolute error percentage. The first thing to keep in mind is that since we're using log 10 instead of log base e, we need to raise 10 to whatever the power is to convert our predictions to price and not log price. For example, if we just run predict.lm, our exponential model, these are the log prices instead of the actual prices. So to undo a log, since it's base 10, raise 10 to the power. So we can do this in this line, 10 to the, using the shift 6 symbol, predict.lm model exponential, and these are the prices. It's very important to keep in mind what unit you're using. So these are log prices and these are actual prices. So don't forget to convert. That will come in handy when we're finding the mean absolute percentage error later. Let's say we have the autoregressive model. So as you'll remember, it's MAPE actual, predicted. A problem with doing this though is that for the autoregressive model, the predictions, instead of from 1 to 25, are from 2 to 25 because it's lag. That means there are 24 predictions, but there are 25 actual values. They have to be the same length to calculate it because what R is doing is finding it for each of these points. So to fix this problem, create a new data frame, new.data equals data, bracket minus C1. This is telling R to delete row 1, or rather to make a new data frame without row 1. So if we'll look at new data, there are only 24 observations. So now if we run this function, we will get the MAPE about 14.6. You only need to do this for the autoregressive model because it has different observations because of the nature of it. You don't need to remove the first row for the other types of models like the linear and exponential model. So remember to use the regular data, not the new data for those. For a linear model, you'd use the same format, 100 times your MAPE of data $, whatever your actual values are, and then predict.lm, whatever your linear model is. For the exponential model, it's slightly different. Like I mentioned earlier, because the prices are log prices unless you raise 10 to the predictions, we need to convert them to actual prices because these are actual prices. So to do so, 100 times MAPE, the actual, and then 10 to the predictions. And if we run that, we get our mean absolute percentage error. And lastly, another way to use the predict.lm function with our exponential model is, let's say we want to predict the model at time 25. To do so, you'd follow the usual predict.lm format. Predict.lm, whatever your model is called, comma list, your x variable, which happens to be time in this instance, equals 25. And if we do it without the 10 to the power, we're going to get the log predicted price at time 25. So remember to use 10 to predict.lm to get the actual predicted price, not the log predicted price. If you prefer, though, you can copy what the predicted value is of doing without 10 to the power and then raise it at the end if you prefer, and you'll see it gets the same answer. I just find it easier to do it in one command. So thanks for watching this video. I hope it was helpful.